It flew where no shuttle had gone previously, and when Parker's solar probe dove into the solar crown in fall 2021, it moved toward our host star to within 13 million kilometers. However, now NASA's, once again, Icarus has struck and altogether undercut its previous approach record. But how could this even be conceivable? How might a probe get so close to the sun without instantly catching fire? And, most of all, what scientific insights has Parker's solar probe accumulated in the super-universe of the solar environment? A brief tale from the author's childhood. When I was little, one of my friends suggested that you could simply send a spacecraft on a mission to the sun by covering it in heaps of sunscreen. But since NASA clearly didn't have enough sunscreen in stock, they decided instead to send an extraordinary spacecraft to our mother star with Parker's solar probe to take data about our source of warmth and life to an unheard-of level. But how is it that the famous space agency is, in fact, following in the footsteps of Icarus? And what technical tricks are behind the fact that this time the approach to the sun didn't end in pure disaster? It's well known that the solar corona, the sun's outer atmosphere with a temperature of 1 million degrees Celsius, is a position of cosmic extremes. This region also holds the answers to some of the most significant questions in solar physics. After all, the corona is the source of the solar wind and also drives some of the most fundamental processes in our solar system. One of the greatest mysteries of the corona is its incredible heat. This zone is, in fact, over 200 times hotter than the surface of the sun. But that's not all. In the lower corona, the temperature increases by nearly 1 million degrees within just a couple hundred kilometers of height. It's as if it were getting hotter in a room the further you get away from the radiator. This is hazardous, no doubt, as indicated by the second law of thermodynamics. There is essentially no heat flow from the cooler to the hotter. In other words, the corona cannot be heated by the solar surface but only by an internal process. However, the nature of this process is still controversial. The first hypothesis relies on the magnetic field lines of the sun, which, like stretched-out guitar strings, oscillate back and forth, thereby transferring energy from the surface into the corona. On the other hand, there's the theory that the intense corona heat is due to the sensitive interactions between the magnetic field lines. In these so-called reconnections, the electric fields between the field lines suddenly break down, releasing energy in the form of heat and waves. Ultimately, though, the key to the heat mystery could also lie in a combination of the two, or even more factors. And that's when scientists realized they could uncover the secrets of the solar corona if they sent a spacecraft directly into it. But how did Parker's solar probe not melt? How is this even possible? How does a spacecraft manage to survive not just temperatures of 1 million degrees Celsius, but also a relentless barrage of radiation? At first, it seems almost like a miracle that Parker's solar probe has survived, because there's simply no material that could withstand such extreme temperatures. But after looking into it further, we realize that it is indeed possible to outsmart the searing heat. After all, there's a difference between temperature and heat. From a physics perspective, temperature is a measure of the kinetic energy of a molecule, which is why the air temperature only shows how fast the air particles are moving. Heat, on the other hand, describes the amount of energy transferred by those particles, and it increases with the increasing density of the particle quantity. And this is the very loophole that NASA's engineers exploited. Although every plasma particle in the solar corona has an extremely high temperature, there are very few of them at the same time. Because of this relative spatial emptiness, the surface of Parker's solar probe's heat shield warms up to only around 1,400 degrees Celsius. But this sounds hot enough to turn every unprotected part, the sensitive measuring instruments, into a pile of cinders. To prevent this from happening, the roughly 3-meter-high and nearly 2.5-meter-wide spacecraft was equipped with a 2.5-meter-wide and 12-centimeter-thick heat shield made of carbon foam, which, in turn, is embedded in 2 carbon plates. Moreover, the outer layer of the shield was given a white ceramic coating, a material that reflects solar heat exceptionally well. Thermometer behind the intensity safeguard, as it were, moves to 30 degrees, and to guarantee that the major assurance is generally unequivocally lined up with the daylight sensors along the edge of the safeguard, trigger an alert when they register direct light. The installed computer then rectifies the place of the test, and the parts that can't be permanently protected are safeguarded by an exceptional composite of titanium, zirconium, and more, which has a melting point of around 2,350 degrees Celsius. The tungsten chips and the electrical wiring made the intensity safe. Interesting earth metal niobium also assisted with ensuring that Parker Solar Probe stays in excellent condition and continues to provide us with extraordinary insights into the mysterious universe of the Sun. How Parker Solar Probe made the unimaginable possible. After the spacecraft set out into the vastness of space on August 12, 2018, the moment finally arrived on November 21, 2021, when Parker Solar Probe became the first man-made object to pass the limits of the solar corona exhaustively. This solar limit is defined by the place where the Sun's magnetic fields are no longer strong enough to hold back the floods of particles exuding from it. Furthermore, in numbers, this amounts to nothing less than Parker Solar Probe drawing closer to our star to within 13 million kilometers. No other spacecraft has ever come so close to the Sun, and considering this historic achievement, NASA specialists discussed a great moment for solar research. The fact that this previously unfamiliar obstacle had been successfully overcome was apparent to the specialists from the measurement data on the magnetic field and solar wind, and from the camera images. Parker Solar Probe subsequently entered a coronal world that only reveals itself during an all-out solar eclipse. And that, multiple times, the measurement data revealed that the spacecraft had passed the corona boundary on different occasions, which in turn confirmed that the supposed Alphane surface is in no way homogeneous and smooth, but rather has local bulges and depressions. However, it's been a couple of days since the first line crossing, so what has happened since then, and where is the probe today? Well, we don't know what you did on Christmas Eve, but Parker Solar Probe moved toward the outer layer of the Sun, a distance of 6 million kilometers on December 24, 2024, setting a new record. Yet again, considerably more reassuring was the news that arrived at NASA a week later, the Solar Rendezvous. The probe reported that all of its instruments were working perfectly and that it was also completely flawless. However, researchers will need to be patient before they can begin to assess the data collected during the procedure. Parker Solar Probe won't begin to send the long-anticipated datasets to Earth until sometime later in January, when its position and orientation are better. In the future, 2 more close flybys of the Sun are planned, but before that happens, let's review the scientific discoveries of the mission so far, from curves to newfound structures. As a matter of fact, the first major finding happened 2 years before the spacecraft entered the corona. While Parker Solar Probe was still heading toward that part of the solar atmosphere in 2019, its measurements revealed a stunning phenomenon. The solar wind has what are known as curves and, consequently, twists, or conversationally, clamshell bends in the particles and magnetic flows. While these countless kilometer-long S-shaped snares clearly increase in number the closer you get to the Sun, the space experts initially did not understand the foundation of the brief curves happening in thick groups. Eventually, this mystery was solved with the help of the ESA Solar Orbiter spacecraft, which captured one of these striking S-shaped curves in the plasma directly in picture form in spring 2022. In combination with the gathered data, the specialists concluded that the bends occur where open and closed solar magnetic field lines come in contact with one another. The most extreme of these so-called exchange reconnections present themselves in the characteristic S-shape and show up in the measurement data as magnetic field inversions. Besides, the bend data gathered by Parker Solar Probe and Solar Orbiter also matched a previously completely unknown structure that cosmologists recognized in the solar corona. This is a unique organization of intertwined plasma strings, whose connection releases magnetic energy that accelerates the solar wind particles. Speaking of the solar wind, a couple of months ago, Parker's Solar Probe and Solar Orbiter were even able to explain a decades-old research question and find the speed setter of the solar wind. In fact, the probes had examined one and the same solar wind stream from different distances and understood that initial magnetic field motions are converted into heat and speed further out. And now, you can convert your click into a subscription. Press subscribe now to never miss a new video from us again. We'll see you soon.